Okay, so in 17.2 we're going to talk about conjugated dienes. And we're going to talk about their synthesis, we're going to talk about the bond length in the conjugated diene and their stability and the different conformations that they take. Starting with synthesis. Synthesizing a conjugated diene isn't any trickier than synthesizing a regular alkene. You can synthesize a conjugated diene if you have a molecule that has an alkene already present and then a good leaving group. You could do an elimination reaction. It'd be best to use something like tert-butoxide for this reaction, because if you use a smaller nucleophile, you're also going to have competing substitution reactions, like if you were to use something like methoxide. Methoxide is a nucleophile that will do both substitution and elimination, so you're going to get a little bit of elimination product, and you'd also get some substitution product as well. This is a review, so if this reaction looks unfamiliar, look back to the alkene chapter. Here's another example. And again, we're using the bulky base tert-butoxide because tert-butoxide does not do substitution. So by using that particular base, we're forcing the reaction to do an elimination, and we don't have to worry about any byproducts. So let's write that down. Use our bulky base to avoid substitution, which is not what we want. Also realize that the leaving group, the halogen, has to be on a carbon that's adjacent to the double bond. Otherwise, when you do the elimination, the double bond is not going to end up being in a conjugated position. If the halogen was, like, say, over here, then the double bond, well, that's maybe not the best example. If the halogen was right here, still could end up, this is just a bad example. If the it looks like there's no way to make a non-conjugated diene with this particular molecule. But if the halogen was in a different molecule in a different spot, you could end up placing the double bond more than one single bond away, which would give you an isolated diene. You don't have to start with an alkene. You can start with a dihalide, a molecule that has two halogens present. If you choose to start with a dihalide, again, you're going to want to use the bulky base to avoid a substitution byproduct. And you want the halogens to be adjacent to each other, again, in order to ensure that you get the conjugated diene. Now we're going to talk about the bond length. In the diene, in the conjugated diene, the carbon atoms in any carbon-carbon double bond, in any alkene system, the carbon atoms are sp2 hybridized. And in Gen Chem, you learned that the sp2 hybrid orbitals are more S-like than the sp3 hybrid orbitals. So and because they're more S-like, the hybrid orbitals are more S-like, that means that they're not as elongated, they're shorter and rounder. And this means that in the double bond, the two carbon atoms have to come closer together so that their orbitals can overlap, because their orbitals are a little bit shorter. This means ultimately that the carbon-carbon double bond is shorter than a carbon-carbon single bond in just a regular molecule. And this is something that we talked about tons and tons. And interestingly, in a conjugated diene situation, the carbon-carbon single bond that is in between the two alkenes, those are sp2 hybrid carbons as well, because those carbons are also part of an alkene, which means that the single bond that separates the two double bonds in a conjugated diene is actually shorter than a regular single bond. So in a conjugated diene, let's just use this one for example. That carbon atom and that carbon atom are both sp2 hybrids. So their orbitals are more S-like and shorter and stubbier, and that means that this carbon-carbon single bond is also shorter than what we would expect. Because it's not, even though it's a single bond, it's not coming from sp3 hybrid orbitals. So, for example, in this molecule, this carbon-carbon single bond is shorter than this one or this one, because this carbon-carbon single bond is formed between two sp2 hybrid carbons. This one is formed between an sp2 and an sp3. This one is formed between two sp3s. So these two single bonds are longer than this single bond over here. Just to give you some data, not that you need to remember this, a typical carbon-carbon single bond is 133 picometers. A typical carbon-carbon single bond is 153 picometers. And the single bond in a conjugated system is 148 picometers. So it's somewhere in terms of length, it's somewhere in between a single bond and a traditional single bond and a traditional double bond.